So this is the formula for our general term. That's a good piece to know because may need that in a minute. But what we want to do is we want to develop a formula which allows us to demonstrate that instead of just saying hypothetically this actually goes to 1 intuitively. Intuition is great in math, but at some point we want to prove it. So we're going to use this formula to help us. So here's what we're going to do. I'm going to erase all this because this is getting in the way now. Do you have that? I'll leave that. Let me rewrite this up here so I have a little more room. I'm going to say that my sum, I use capital S for series. It also stands for sum. So I'm adding up all my terms. So here I have a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub r, not a sub r, a sub 1 r cubed plus, and eventually I have my last term, a sub 1 r to the n. This isn't an infinite series yet. We'll do the infinite series piece in just a second. And actually this should be n minus 1 because we have n terms. So if we have n terms using the formula we had here, the power at the end is 1 less. So far so good? Now what we want to do is we want to come up with a formula for adding this up. Because if I asked you, this was kind of a pain, if I said, well, what's the next one? If I added on 1/32nd, what if I added on 1/64th? What if I added on 1/128? It gets to be a bit taxing to have to add this all, right? So the question is, can we come up with a formula for a geometric series, the common ratio here is 1/2, to add up the first 27 terms easily? And that's what we're working on over here. We're going to see if we can develop a formula. So I look at this and I think, well, is there any way I can eliminate these terms? Because the problem is I have all of these terms in between. And for example, if n were 27, that's a lot of terms. I don't want to add up 27 stuff. Well, what if I had 1,000 terms? Ugh. I certainly don't want to do that. So what I do is I take a look at this and I pull out what's known as a parlor trick. I say to myself, what happens if I multiply all of these terms by r? So just humor me, let's do it. We'll multiply everything. Oh, there's my fancy pen. Remember that one? High quality pens, no ink. Nice white core. Put that one over there. This one I just tossed down, that's good. Let's multiply this series by r. If I multiply the series by r, then I get r times s of n on this side, right? You remember this m? Shaky, but it looks familiar. Okay, well, M, then you get to be my assistant. We'll make this unshaky. We'll make this unshaky. So if I multiply this whole series by r, what's the very first term I get? I'm going to multiply this by, and this by, and this by.
So now
Yeah, see, you do remember. So I'm going to multiply by r, so what's the first term I get over here? The first one I get is a to the 1 r. Why? Because I multiplied this thing by r. That's a terrible arrow. And so I get a1r, right? Then I multiply this one by r, and I get a1r squared. Oh, it happens to be that one there. And I'm lining these up for a reason. And then when I multiply this one by r, what do I get? a1r cubed. Plus, and then I get an a to the r n minus 1 term, and what's my very last term? M. When I multiply my last term by r, what do I get? A r to the n.
Just kidding. Okay.
Right?
Yeah.
So now here is where the parlor trick part comes in. I notice that, oh wow, look, I got an r and an r squared and an r and that term. I wonder how I can get rid of them. I know, how about if I just subtract everything? So I'm going to, instead of leaving this positive, I'm going to subtract this. I'm going to multiply this whole equation through by minus 1. So now that's negative, that's negative, that's negative, that's negative, that's negative, and now I'll add them. So when I add these two together, what do I get? I get Sn minus r of Sn Yes?
You can group that. You'd say S.
Well, we're going to do that in just a second, right? You're a step ahead. Well done. So I just subtract these. Now what happens when I subtract here? Well, I have 0 here. So I get a sub 1. What happens when I subtract these two? They cancel, 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 cancel. All of them cancel. And what am I left with at the end? Here, since I'm adding these up, I get plus 0, plus 0, plus 0, plus 0, plus 0, plus 0, blah, blah, blah for as many terms until I get down here, and then I get minus a to the Rn. So that means S of n minus Rs sub n equals a sub 1 minus a, and this should be a sub 1 also. These should all have subscripts of 1 on them. A sub 1 R to the n. Now, Mirror 2, you made a suggestion. What was your suggestion?
You group S n minus R times.
Yeah, we can factor out S sub n. S sub n is just a constant. It's the sum of the series. And that sum, if it's finite, is just some number. It's a constant, so we can factor that out. So we get S sub n times 1 minus R equals a to the first, or a sub 1 minus R sub 1 R to the n, and then what do I divide by? Then I take this and I divide this down here, 1 minus R, erase it off this side. That's our formula. So if I want to know what the sum of the first n terms are of a series, I use this formula. And it can also be written this way. You can factor the a sub 1 out. I like doing that because it helps me remember the formula. I get 1 minus R to the n over 1 minus R. I like the way that looks better because these two look the same except for the n power there. And I just personally find it easier to remember it that way. Some books will actually reverse the order because you can factor a negative sign out of these two and they'll put the R sub n minus 1 over there and the R minus 1 here just because they like putting this over here. I don't, because then it doesn't help me remember how to derive the formula in case I forget it. But you see, if I factor a minus sign out of it, these two terms would switch, and those two would also switch. So this is our formula. So let's come back here for a second, see if the formula actually works. And put the formula up here. We have S sub n equals a sub 1 minus R to the n power over 1 minus R. Okay, so here we have the first 4 terms. Let's see, we just did these by hand. Let's see if it works. So if I wanted to know what S sub 4 is, that means the sum of the first 4 terms. If we did this right, it should come out 15/16. So Mirror 2, what's the common ratio?
Of this?
Yeah.
1/2, 8.
Yeah, it's a half. So our common ratio R is a half. Okay, so good enough. So S is 4. So this equals, what's our first term, a sub 1? Look up here, right here. Yeah, our first term is a half. So a sub 1 is a half times 1 minus, what's the common ratio? A half. Oh, a half to the 4th power. All over 1 minus a half. This simplifies to a half, so I have a half times 1 minus 1/16 over a half. The halves cancel. I get 1 minus 1/16, which is 15/16. Now, just work with me here for a minute. Let's go out to the nth term, right? The common ratio, R here, is always going to be a half, right? My first term was a half, so these two will always cancel out.
So it's just...
I'll just be left with 1 minus R to the n.
Yeah.
So if I say, what's the sum of S27?
Wait, is that true for all cases?
No, just this case.
Okay.
Just this case. But my point is, you notice the pattern was 3/4. There's one difference. Here's 7/8, one difference. 15/16, one difference. Why is that? Well, the reason is I always have a 1/2 here because that's my first term. I'm always going to have a 1/2 on the bottom because r is a half in this case, so these two always cancel out. So what am I left with? I'm left with 1 minus 1/2 to the n power. So this will end up 1/16 or 1 over 32 or 1 over 64. So since if this is 1 over 64, when I subtract 1 over 64 from 64 over 64, I get 63 over 64. So the number is always going to be one different. That's in this case, not in general. That's why the pattern is like that. Does that make sense? Okay, now is the moment for the drum roll.